Welcome to another edition of Coonrod's Corner. Today's topic, Impedance Tradeoffs, what needs to be considered for optimum circuit performance. And now here's your host, John Coonrod.
Hello, welcome to Coonrod's Corner. My name is John Coonrod. I am a technical marketing manager for Rogers Corporation. Today I'm going to be talking about several different aspects of impedance and specifically different facets of impedance that the designers and the fabricators really should understand for optimum circuit performance. Now, there's several different categories for impedance. There's wave impedance, there's characteristic impedance, surface impedance, frequency-dependent impedance. There are several different types of impedances, and really mostly what I'm going to be talking about today is characteristic impedance. And characteristic impedance in a practical sense is typically what's measured at the printed circuit board fabricator. So some of the fabricators will have a printed circuit board that is a controlled impedance board, and before they ship it they have to prove that it is within the range of impedance that it's designed to be. So maybe it's 50 ohms plus or minus 10%, so they'll measure that using a TDR, time domain reflectometer, and the impedance that they're actually measuring is the characteristic impedance. And that's mostly what I'm going to be focused on today. So to begin with, let's go through some of the basics of impedance. Shown here is a circuit and also a schematic that is representative of the circuit. And the schematic is a RLGC schematic. And what that means is R is resistor, L is inductor, C capacitance, G conductance. And I have that drawn over a circuit, which is actually a microstrip transmission line circuit. And the symbols are really drawn there to show you the characteristics of the circuit related to the schematic. This is really not a rigorous definition, obviously, but it's really to give you an impression of how the schematic relates to the circuit itself. So the signal conductor is related to the series resistor and series inductor, and then the capacitance is related to the shunt capacitance and also the conductances as well, but that's actually in the dielectric itself. So the dielectric or the substrate material is related to the capacitance and the conductance, and the signal conductor is related to resistance and inductance. The drawing shown here is just an expansion of the last drawing, really showing a little bit more of how the electromagnetic software that does these types of models are looking at the circuit. And what they're doing is typically field solving. So they're field solving slices of the circuit. So infinitely thin slice they will solve for the fields and then move up the circuit a little bit farther in length and solve it again, move up the circuit farther in length, solve it again, and then piece it all together to get the overall performance. Now the formula that I've shown here is similar to the last formula, but this formula actually has loss characteristics included. So the R is loss characteristics related to the conductor, G is loss characteristics related to the dielectric material, so dielectric losses. These basic impedance formulas that I've given are really used for reference, and it's good to keep in mind when you're going through design or even troubleshooting, just to understand the relationship. And here in a few minutes I'll go through that in a little more detail to give you a feel for how you can use these formulas. But also what I want to talk about is when the impedance is actually measured with the TDR, time domain reflectometer, normally what it's doing is measuring a reference cable, like a 50 ohm cable, and then the probe will be put onto the circuit, and then the circuit's tested, and whatever the impedance of the circuit is related to the 50 ohm cable. And if it's lower impedance or higher impedance, it's really in relation to that 50 ohm cable usually. There are several different techniques, but that's one of the more common ones. The simple impedance formula gives you a good idea of the relationship between capacitance and inductance and how that relates to impedance. But also I wanted to go through a quick example of impedance measurements where the 50 ohm on the left side of the bottom chart is showing the reference cable, and then we get into an area to the right of that which is lower impedance, 45 ohms, and typically that is the term used for that is capacitive. So when you have a lower impedance compared to the reference, they usually consider that to be capacitive because an increase in capacitance means a decrease in impedance, as you can see in the formula. And then as you move to the right from there and get into a region of the circuit that's 55 ohms, then that's obviously higher than the reference. And in this region, the term would be inductive, so the circuit is acting inductive. So the reason why that is, increase in inductance is directly related to impedance, so as inductance raises, so does impedance. And then to the right of that again is the 50 ohm reference cable. So now let's think about some of these relationships quickly, and that is, to begin with, let's look at a substrate thickness of the circuit. If you were to look at a thin circuit compared to a thick circuit, basically you're moving the copper planes farther apart as you go thicker, and when that happens the capacitance is decreasing, and a decrease in capacitance means an increase in impedance. So when you go from a thin circuit to a thicker circuit, you're going to increase the impedance. Now another relationship would be the conductor width, so the signal conductor width. If the signal conductor width is narrow and then you make it wider, going from narrow to wider, that means the parallel plate capacitance between the signal plane and the ground plane is increased. So you have an increase in capacitance. So a wider conductor increases capacitance. Capacitance is inverse related to impedance, so impedance decreases. Wider conductor, lower impedance. So that's some basic relationships. Now there's also several variables that can be very important to understand and how they relate to impedance. And there's really a hierarchy of these variables and the order of which they impact impedance. And it's really good to understand this in troubleshooting and also in the design phase. The table of information that I have shown here is actually just doing simple impedance models, and you can use an impedance model that we have on our website, or also you can download it from our Rogers Technology Support Hub, which is MWI 2017. So an impedance modeling software will give you the output of the table of information here, and really what I did was the first row of information is the baseline circuit. And what I did was I started off with a material with a dielectric constant of 3.5. The substrate thickness is 20 mils. Copper thickness, overall copper thickness, is 2 mils. The conductor width, 43 mils, and that gives me a characteristic impedance of roughly 50 ohms, 50.07. So that's my baseline, and then now I'm going to make some comparisons to that. So the next row of information down is the same setup, except now what I've done is decrease the substrate thickness by 10%. So now it's 18 mils thick, and you can see the change in impedance on the sixth row. It shows the difference in impedance of 3.21. And then put the model back to the reference, and now the third row down, we change only the dielectric constant from 3.5 to 3.45. The reason I chose that number is because Rogers has several materials in that range of dielectric constant with a tolerance of plus or minus 0.05, and that's considered a pretty well-controlled dielectric constant for a material. So when you change just the dielectric constant by 0.05, the difference in impedance is 0.32. And again, put the model back to the reference, and then the next line down we look at only the copper thickness change, and you get the idea at this point. And the next line down we also make a change with the conductor thickness and the conductor width. So really the summary of this table information is shown above, where the most significant variables in order of significance is substrate thickness, conductor width, copper thickness, dielectric constant. So in some cases, the dielectric constant and the control of the dielectric constant may not be as critical as the substrate thickness. And understanding that in the troubleshooting phase or even the design phase can be very important to know. The measurement of impedance for a circuit has a lot to do with the rise time and when it comes to accuracy. So the faster the rise time, basically, the more accurate the impedance measurement is going to be. And it's not just for impedance of like a transmission line. It could be structures that have varying impedance, where you have different impedance values on a particular circuit. So having a machine that has very high rise time, a very fast rise time, is very beneficial to having accurate results. Now, I did a study a while back that really proves the point of the importance of rise time, and it was really in regards to a right angle conductor routing. So I've read over the years that some people would state that a right angle really has very little effect on impedance, and I disagree with that, but it has to do with the rise time. If you have a very slow rise time, you would not be able to perceive the difference in impedance. A faster rise time, you can. So I did a quick study on this using a strip line structure, and the signal plane had a S shape to it, to where I had 90-degree bends in 2 different points. And in those areas, I tested it for impedance, and I was looking at the impedance output using different rise times. So shown here are 4 different screenshots of the same circuit being tested and with different rise times. The screenshot in the upper left is the slower rise time at 35 picoseconds. And you can see here you have very slight impedance anomalies in different areas. And marker 2 and marker 3 is actually the 90-degree bend areas as shown in the picture to the bottom right. And in the upper left picture of the screenshot with the rise time of 35 picoseconds, you really cannot see the features there very well. Now testing the same circuit with a faster rise time, and that's the bottom left picture, rise time of 17.5 picoseconds. Now you're starting to see a little more definition of those right angle bends. And then speeding it up a little more, upper right picture is showing rise time at 8.7 picoseconds. And then finally, bottom right is the fastest rise time of 5.2 picoseconds. And you can see when you have very fast rise time, it's very sensitive to these differences in impedance due to these 90-degree bends. And now marker 2 and marker 3 is showing very distinct differences in impedance, and actually these are capacitive dips. So each one of these bends are an increase in capacitance. That concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you are not already a member, join the Rogers Technology Support Hub and gain access to calculators, technical papers, and more of Coonrod's Corner and other informational videos. Rogers technical information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.